I don't know what that does. Okay, so the grades are up for your exam, and if you haven't picked them up already, you can pick them up in my office whenever I'm in there. And I do have up all the information for your iClickers, what you sent me, so you can see what you got wrong, what you didn't, and if for some reason you didn't send some to me, pay attention to that, so you know that mostly only one or two things were sent incorrectly, so just pay attention to that. Overall, you have been using the iClickers well, and I'm pretty happy with the overall grades. Most of you guys got above a 70, so I'm pretty happy with that. And of course, your iClicker points, you can see that on your exam. It says in-class bonus. That's from your iClicker points from in-class. So if you haven't been coming to class or you're not answering your iClickers, you won't have any bonus points from that. So when you look at your test, I have a little thing that says iClicker bonus, and those possible 3 points are there. And there's a couple of people that got 3 points, so that's good. We're starting with chapter 4. Honestly, the balancing equations we did at the end of chapter 3, I don't really understand why it's not in this particular chapter, because we're really starting out with looking at equations in this chapter and figuring out some things based on equations, like how much reaction we expect, how much products we expect to make. So 4.1 is not really anything. 4.2, all those first little sections of every chapter is just a relation to everyday things, and you can read that. But the main thing, we already talked about law of conservation of matter, and we know that matter is not created or destroyed in a chemical reaction, but it can be changed, and that's what we're seeing. So we already talked about balancing our chemical equation, which illustrates our law of conservation of matter, which is why we worked on those balancings. So in a balanced reaction, our total mass of reactants is going to equal to our total mass of products, assuming, of course, we have a full reaction that occurred. And a balanced reaction has the same type and quantity of atoms, though how they're arranged in molecules are going to be different. So that's what we see. So our stoichiometry is the first thing we're going to be looking at. And that's based on this law of conservation of matter. Stoichiometry studies our quantitative aspects. So there's qualitative, that's just noting differences. Quantitative is actually looking numerically what we expect to happen in a reaction. And we can use our reaction stoichiometry to predict how much products we expect, to, if we know how much products we want, how much reactants we have to start with, things like that. And that's all based on those coefficients that we get to when we balance our equations. So we're going to start with a quick iClicker question. So we can get a lot from our chemical equations. We know from a chemical equation that's balanced how much water molecules we need to react with CO2 molecules. We know based on our chemical reaction how much O2 we expect to form. So we can learn a lot from our chemical equations and our balanced chemical equations. If it's not balanced, of course, that's always going to be your first step. So what does this equation mean? Let's look at this example. We have iron solid that's reacting with our O2 gas to form Fe2O3. So what this means is that if we look at this in terms of atoms, we need 4 atoms of iron plus 3 molecules of O2, because of course that's not in its elemental form, to form 2 molecules of Fe2O3. Now, this isn't really a useful relationship typically, so instead we can use this as moles, where, remember, moles is just our way to relate things. So where we can say 4 moles of iron is going to equal or need 3 moles of O2. Because if we have our mass, we can calculate our moles. And if we have our moles, we can calculate our mass. So that's a much more useful relationship than talking about our atoms and our molecules. And that's going to form 2 moles of our product, in this case Fe2O3. So this tells us some information about our molecules. This also tells us that for every 4 moles of iron, we need 6 moles of oxygen atoms, because in every oxygen molecule, we have 2 oxygen atoms. And that means we're going to form 4 moles of iron and 6 moles total of oxygen, because we have 2 iron atoms and 3 oxygen atoms in our final compound. So we have a lot of relationships that we have with just this chemical equation. And of course, we know that iron's a solid and oxygen's a gas. So if we had a full reaction, now again, if we have a full reaction, 23.4 grams plus 96.0 grams of O2, the question is how much Fe2O3 we can make. And we can make some, we can do some calculations for that as well. So total, we have 415.4 grams of reactants, so that's how many products we're going to have. Now remember, we have different amount of moles per grams. And remember, we need 3 moles of O2. So we need a balanced reaction before we can do any stoichiometric relationship. So our reactants and our products can be a relationship. Our reactants and reactants, we have a relationship between them, and our products and products, we have a relationship. And depending on what we need. So let's say I have 50 grams of O2, and I want to know how much product I can make. So I can have a relationship between that reactant and my possible products. Or let's say I want to react 50 grams of O2 to completion, so then I need to know my relationship of my reactant to my other reactant. How much of a ratio I need of both of them. And of course, if I know how much products I have, I can reactants I have, I can figure out how much products. So that might be a relationship I need. Or if I know how much product I need, let's say I am, for some reason, making a specific thing, making a drug, and I need a certain amount of it, I know how much reactants I need to start with to get that amount. So these relationships can all be related, but depending on what I need them for, I might do a different one. Now remember, if we're doing these relationships, we can't relate our mass to our mass, because our different atoms weigh different amounts, our different molecules weigh different amounts. So if I'm trying to say I want 50 milligrams of product, let's say, I really can't do that relationship stoichiometrically in grams. I really have to convert that to moles, because my moles are relatable, but my mass isn't, because my product might have a different mass and likely will have a different mass than my starting materials. And they're not relatable because my atoms have all different masses. So what I have to do is convert to moles first. So if a mass is given, I have to convert to moles, and we can do that with either the atomic mass if we're talking about an atom, or the molecular mass if I'm talking about a molecule. And we know how to calculate that already. If I'm getting a volume, then I can use molarity. Now right now, we're going to get into that more in this chapter, because this chapter, after we talk about chemical reactions, we're going to be focusing on solutions. So that's our compounds dissolved in a solvent, and in this class it's going to be typically water, though in other classes it could be other solvents, but for this class it's going to be mostly water. So we're going to talk about what molarity is, and how we can convert our volume to mass. Now if we're talking about, let's say, a pure compound, and a pure substance and I have its mass, or I have its volume, I could also use its density to convert to mass. Because remember, density is related to mass and volume. So let's say I'm told I have 30 milliliters of water. I can convert that to mass using my density, and then I can then convert that to moles. So I might need to use density if we're talking about a pure substance. You don't have to really memorize using molarity right now. We'll be getting into that more later. Our stoichiometric factor is what relates our different parts of our chemical equation to each other. Now sometimes that won't change the number if we have a 1-to-1 mole ratio, but oftentimes we won't, so I always want you to include this step in your conversions. That way you don't make a mistake when it does matter. And often it will, because you won't always have a 1-to-1 ratio. So we're going to relate this stoichiometric method to making pizzas because I like my little guy. He's a happy guy. So first off, for this discussion of relating this to making pizzas, there's two things I want you to imagine. One is that you cannot deviate from the recipe. Because you can't deviate from the recipe in your chemical equation. So you're equating your chemical equation to a recipe. Now we know in general you can change your pizza recipe, but let's just pretend you cannot change the recipe, and whatever the recipe calls for, that's the only way you can make a pizza. So otherwise this relationship doesn't really work. So the number of pizzas you make depends on the amount of ingredients you use. So let's say that this is our recipe. We need 1 crust, 5 ounces of tomato sauce, and 2 cups of cheese to make 1 pizza. And again, for this to work, you have to imagine that we cannot change this recipe at all. So we can't make a different size pizza. Then our relationship can be expressed as, for every 1 crust, we need 5 ounces of sauce, we need 2 cups of cheese, and that is going to relate us to 1 pizza. And if we don't have that, then we can't get our 1 pizza. So that same relationship can be applied to a chemical equation. When we look at this chemical equation, you don't really need to know what C8H18 is. You should be able to balance this, but it's already balanced. You can always double check that. And we see we have 2 moles of C8H18 for every 25 moles of O2, and we need that to make our 16 moles of CO2 and our 18 moles of H2O. So our relationship, for every 2 moles of C8H18, we need 25 moles of O2 to react. So that's our stoichiometric relationship. We also have a relationship between our moles of one of our reactants and one of our products. So for every 2 moles of C8H18, we can make 60 moles of CO2. Or we can make 18 moles of H2O. Also, we know for every 25 moles of O2, we can make 16 moles of CO2 or 18 moles of H2O. And we also know whenever we form 16 moles of CO2, we're also going to form 18 moles of H2O. So we have these relationships just from our balanced equation. And which one we need is dependent on what we're trying to do. So when we look at this one, what's our mole relationship between glucose, which is C6H12O6. I don't expect you to memorize that's glucose. Of course, that's glucose. And H2O. We see, and this is balanced, but you first want to always check that it's balanced. In this case, it is. That we have 6 moles of H2O for every 1 mole of C6H12O6. So that's B. And this is just our relationship. So I can put 6 moles H2O equals 1 mole C2H12O6, or I could put 1 mole C6H12O6 is equal to 6 moles H2O. That's the same relationship. There's no difference. So it's a 1-to-6 ratio, and that's what's really important. It's also important that we don't switch those numbers. It's not a 6 mole C6H12O6 to 1 mole H2O. That's not what our relationship tells us. So don't switch the numbers. Keep the coefficient with the molecule or atom that the relationship of the chemical equation gives you. So we can use these relationships to predict how much of a product we can make. For example, let's say we have 6 cups of cheese. we can figure out how many total pizzas we can make based on our relationship of our, in this case, recipe. So we know that for every 2 cups of cheese, we can make 1 pizza. So if we have 6 cups of cheese, then I can use my relationship that for every 2 cups of cheese, that equals 1 pizza as a conversion factor. I need my cups of cheese to be at the bottom so they cancel out. And that tells me that I can potentially make 3 pizzas. It's not telling me that's how many pizzas I'm going to make, but based on 6 cups of cheese, I could potentially make 3 pizzas. I need to know more to know how many pizzas totally I can make. So it's assuming I have enough of everything else. So our amounts of other substances in our chemical reaction can be determined by just one substance. So for example, this is best shown as an example. If we're given an equation and I want to know how much CO2 can be made from 22.0 moles of C8H18 and our combustion of C8H18. So for this one, this is a combustion. You should be able to write this. There's some chemical reactions I don't expect you to know how to write. And that's okay, and I'll give those to you when it's important. I'll give you the reaction. But combustion we've been talking about. So the first thing is we need to have our chemical equation. We can't really do this reaction without a chemical equation. So we know combustion is our carbon-containing molecule, C8H18, plus O2 to form CO2 and H2O. And we looked at this reaction earlier, and again, you should be able to balance it. I'm not going to go through balancing it, but definitely practice all of the equations I show you. Practice, make sure that you can balance them. So I have my relationship. Now the question is, which relationship am I going to be using? Well, I'm told how many moles of C8H18 I have. I have 22 moles. And I want to know how many moles of CO2 I can make. So my relationship is going to be between C8H18 and CO2, because that is the relationship I'm being asked about. So I know I have 2 moles of C8H18 for every 16 moles of CO2. So I can set up this as a relationship. I'm starting with 22 moles C8H18. So my 2 moles of C8H18 is going to be at the bottom. Again, it's really important I include my molecule, because moles of CO2 cannot cancel out moles of C8H18. So I want to include that C8H18 and CO2 in my relationship so I don't put the wrong number at the bottom. So remember that 1 mole, the 2 moles is tied to C8H18. That's my coefficient for that molecule. And remember, this is a mole relationship. So I know my 2 goes on the bottom because otherwise C8H18 would not cancel out. Now you can, if you want, reduce this to 1 and 8, but you don't have to. It does that when you do your calculation. So and whenever I do my work, I keep my coefficients exactly like they are. But it's not wrong to say my lowest ratio is for every 1 mole I get 8 CO2, because that's the same thing. So that means I could get 176 moles of CO2. Now this isn't grams. I could calculate that to grams, of course, with my molar mass. The chemical equation is given to you. And I'm going to give, a whole minute for this one. There we go. Not touching it. this up. So let's go through an example. According to this equation, how many moles of water is made from the combustion of 1.0 moles of glucose? So I'm given the equation. The first thing I always want to do is make sure that the equation is in fact balanced. And it is. I am telling you it is, but that's your first thing you always want to check. So make sure that it's a balanced equation. Now typically if coefficients are there, it should be balanced, but you always want to double check. So in this case it is. So here I'm relating glucose, which is my C6H12O6, and of course, if you didn't know that was glucose, you could use process of elimination. You know carbon dioxide, O2, and water, so clearly the other thing is glucose. So I'm relating my glucose with water. So the first thing is, what's my relationship? And my relationship is that I have, well, first I know I have 0.010 moles glucose, and I'm finding my moles H2O, so I need to convert my moles glucose to my moles H2O, and I'm going to just be using the relationship that's given to me in the equation. So, according to my equation, I have 1, and remember, we don't ever show the 1 mole C2H12O6 for every 6 moles H2O. Also, my amount of C6H12O6 is given to me in moles. Now remember, if this was given to me in grams, I'd have to do a conversion first, because I cannot relate grams of one thing to grams of another, because our molar masses are different. So if I was given grams, I'd have to calculate that to moles first. But I'm not, I have moles, so I can start with and I am going to write down C6H12O6. This might add like a half a second to my writing, but it's going to help me to avoid making mistakes later on. So my moles in my relationship of C2H12O6 is going to go at the bottom. And that means my moles relationship of H2O from my equation goes at the top. So I can cancel out moles of C6H12O6, and that's how I know which number goes at the top or goes at the bottom, because moles H2O cannot cancel out moles C6H12O6. I need that relationship. So I can make possibly 0.60 moles of H2O. And of course I started with my 2 significant figures. So my final product is in my 2 significant figures. Now remember, my ratio is going to be infinite significant figures. I didn't measure 1 to 6. That's just a ratio. So that has infinite significant figures. You don't need to worry about using that. Just use your measurements as your significant figures, because your coefficients are exact. For every 1 mole of this, I get 6 moles of that. So we consider that infinite. Let's look at this. Let's say in 2006, we combusted 3.5 times 10 to the 15 grams of petroleum. And we want to estimate our mass of CO2 produced in 2006. So first off, this is given to us our ratio of petroleum to CO2. I'm not telling you what petroleum is. I'd need to. I'd either need to tell you what the average organic molecule looks like, so you know its formula. So in this particular thing, you don't have enough information unless you know what petroleum looks like. But assume gasoline is octane. Most of it is. Not all of it is. So what we have is C8H18. So our combustion, once we balance that equation, will be 2 times C8H18. plus 25O2 gives us 16 CO2, 18 H2O. If I wanted you to do this, I have to give you this. I wouldn't just say petroleum. So you don't have to memorize petroleum is mostly octane. That's not necessary. So what this is relating is our moles of petroleum with our moles of CO2, not our mass. So here we will have to do a calculation with our mass. Otherwise this won't work because we cannot relate our mole relationship is not a mass relationship. Because C8H18 has a different molar mass than CO2. So we do have to convert these to moles. So our first step is, if we don't know our molar mass, to calculate it, because we're given our gram relationship. So our first step is to calculate how much moles of C8H18. If we know how much grams we started with, we could calculate moles, which we've done in earlier chapters. And we do that using our molar mass, which we also know how to calculate based on the periodic table. Once we have our moles of C8H18, then we can use our relationship of our equation to convert our moles of C8H18 to whatever. And this case is asking about CO2, so we're going to convert to moles CO2. Once we do that, then we can convert our moles of CO2 back to grams, because our question wants it in grams. And then if we wanted kilograms or something else, we can do that. But right now, this is only asking for grams. So for this conversion, we need our molar mass of C8H18. For this conversion, we need our molar mass of CO2. But this conversion is our conversion of this particular reaction. And remember, this is only true for this reaction. Another reaction won't have the same stoichiometry. So we know how much grams of our petroleum we're starting with. And we want to find grams of CO2. And we just talked about our conceptual plan. So first off, I'm not doing this right now, but make sure you can do this on your own when you go home. My molar mass of C8H18 is 114.22 grams per mole. That means I have 114.22 grams of C8H18 for every mole of C8H18. Don't say I have 114.22 moles of C8H18. That's incorrect. It's grams per mole. So that many grams per every 1 mole. And then my molar mass of CO2 is 44.01 grams per mole, which means for every mole of CO2, I have 44.01 grams of CO2. My other relationship is from my equation. I know from my equation I have 2 moles of C8H18 for every 16 moles of CO2. So I can use that in this relationship. So starting with my grams of C8H18, I want to my grams to cancel out, so I'm going to put my 114.22 grams C8H18 at the bottom. And that converts it to 1 mole C8H18. So my grams C8H18 cancel out. And again, the molar mass comes from the periodic table and the fact that I have 8 carbons and 18 hydrogens. Bless you. So now I want to convert my moles of C8H18 to moles of CO2. And again, I have that relationship. Now my moles of C8H18 are going to go at the bottom, and that coefficient is 2. And at the top is going to be my relationship to my moles of CO2. So remember, moles of CO2 cannot cancel out moles of C8H18, so that's how you know what goes on the bottom, what goes on the top. So if I wanted my moles of CO2, I could stop there, but we want grams of CO2, so I have to use my molar mass conversion to then convert this to my grams. If you're following your units, you won't have a problem here. But of course, you have to know what your molar mass tells you. It's grams per mole. If you don't understand that, you're going to have a hard time. So my final unit that I didn't cancel out is grams CO2. That's what I want my final unit in, so I set this up correctly. So when I do this calculation, it's going to come out to this number, but I only started with two significant figures, so I have to round that to two significant figures. So based on the amount of petroleum that was combusted, that's about the amount of CO2 that was formed in grams. That's a lot of grams. So looking at this example, this was your iClicker question. Again, here we're told we have a certain amount of grams of Na3. That's just sodium azide, but you don't really need to know that. In fact, for this whole thing, you didn't need to know any of this. None of that was really necessary. If I was telling you to come up with a decomposition reaction, that might be necessary, but as of this point, you don't know how to predict your decomposition reaction products, so I wouldn't expect you to do that. So I gave you the equation. I also gave you the molecular weight of sodium azide, so that's helpful. I might not do that on a test, but this is an iClicker question, so there's time constraints, which is understandable. So I'm given that I have 6 grams of sodium azide, and I want to know how many grams of N2 are likely going to be produced. So I have a relationship, and this is balanced. I have 2 sodiums on each side of the periodic table and 6 nitrogens. So that is a balanced equation. So my relationships, I have a relationship between my grams of NaN3 and my moles of NaN3. That's what my molar mass tells me, or my molecular weight. I also have a relationship between my grams of N2 and my moles of N2. I didn't give you that one, but 14 times 2, because we have 2 nitrogens. So that's I don't know why I put atomic mass of nitrogen, if you look on the periodic table, is 14.01. So I have 2 nitrogens, so I know I have 28.02 grams of N2 for every mole of N2. My last relationship is relating my moles of sodium azide with my moles of N2. Now I could also figure out my amount of sodium, but that's not being asked in this equation. So this is a 2-to-3 ratio, where I have 2 moles of NaN3 for every 3 moles of N2. So now I can set this up. Again, I need to convert this to moles because my relationship of my equation is in moles. And again, that's because we can't relate our mass because our different molecules have different molar masses. So we can do that, and I gave you the molar mass, so I have 65.02 grams. NaN3 go at the bottom, so they cancel out, and 1 mole at the top. Now I can use my relationship for this reaction, this is only for this reaction, between my NaN3 molecule and my sodium gas. So my 2 moles of NaN3 go at the bottom, so they cancel out. And my 3 moles of N2 go on the top. This wants our answer in grams, however, so we have to do one more conversion. And when we plug that in, you will get the answer to be a 3.88. You will not get the correct answer if you do not do this point. So always make sure that you are doing that. It is sometimes necessary that we set up our reaction exactly, where we have the perfect amount of each reactant to fully react. However, sometimes that's not the case. Sometimes you might have more of one reactant than you need to react, and sometimes that's advantageous because, as we'll learn in this class, that Le Chatelier's principle states that if you put in more of one reactant, it pushes the reaction forward. So we're trying to get a full reaction. Not all reactions will go to 100% completion because of energy concerns, and when we talk about thermodynamics in chapter 6, we'll see more details about that. Especially in organic chemistry, we'll see that we don't have a lot of reactions that necessarily go to 100% completion. So we might have one reagent in more than what we need to force the reaction to go forward. So that brings us to some things we're going to be talking about called theoretical yield, percent yield, limiting reagent, and excess reagent. So again, back to making pizzas. So let's say again, this is our equation. And we wanted to know how many pizzas we could make if we had 4 crusts, 15 ounces of tomato sauce, and 10 cups of cheese. So to figure that out, we need to take each of those individually and determine how many pizzas we can make. So based on our 4 crusts, we know for every 1 crust equals 1 pizza. Now I know this isn't changing the number at all, but I always like to do this so I don't make a mistake. So that means that we can make a total of 4 pizzas. But we only have 15 ounces of sauce, and it takes 5 ounces of sauce for every 1 pizza, again, assuming we can't deviate from this equation. So that means the most pizzas we can make with the sauce that we have is only 3. Even though we have 4 crusts, we don't have enough sauce for 4 crusts. And then 10 cups of cheese. Remember, there's 2 cups of cheese for every 1 pizza. So we could make 5 pizzas, but we don't have 5 crusts, and we don't have enough sauce for 5 pizzas. So this is an example that we are going to have things left over after we make our pizzas. And this also can help us determine how many possible pizzas we can make. So this is just what we converted. According to this, the max amount of pizzas we can make with this amount of crust, sauce, and cheese is 3. Because our sauce is limiting the amount of pizzas we can make. And assuming, again, we can't deviate from the recipe for whatever reason. Maybe you work at a chain pizza restaurant, all pizzas have to taste exactly the same. I don't know, whatever. So we only have enough tomato sauce to make 3 pizzas. Once we make all those 3 pizzas, we won't have any more sauce, so we can't continue to make pizza. When we're relating this to chemistry terms, this is what we call our limiting reagent. If we don't have enough of each reactant to fully form our product, then the only amount of product we can make is the amount of the least amount of reactant that we have. But remember, this has to be in moles, because in grams this isn't relatable. So for a reaction, our limiting reactant, our reagent, so sometimes we call reactants reagents. So you'll hear reactant and reagent interchangeably. It means the same thing. Limiting is the big thing. Is the reactant that limits the amount of product. This is the one that tells us we can make the least amount of product. Once we run out of that reactant, we can't make any more product. So that's why it's limiting the amount of product we can make. It gets consumed in the reaction. Anything left over once the reaction stops, that's an excess. That's our excess reagent. Because we have it left over in our reaction, we still have that starting material. So, like I said, some reactions, we won't have a limiting reagent. We'll set it up perfect. But oftentimes we will. So we want to figure that out. So the amount of product that can be made from my limiting reactant, that's my theoretical yield. That's the most yield I could make based on what I'm starting with. Because I can't make more than what I have. Now again, when we're doing this, we won't just say, okay, I have 5 grams of water and 6 grams of sodium metal, so therefore I can only make 5 grams of product. Remember, we can't relate it in grams because our reactants have different molar masses, our products have different molar masses. So what we have to do is relate this in moles. That's going to be really important. So sometimes it's definitely something we're going to have to do a calculation with. It's not going to be very easy to just look at the chemical equation and make the determination. So let's look at the combustion of methane again. This is our combustion of methane, and this is the balanced equation. So if it was set up perfectly where I had 1 mole of C4 for every 2 moles of O2, I'll get a complete reaction. Nothing would be limiting, nothing would be in excess, and my theoretical yield should be 1 mole of CO2 and 2 moles of H2O. But realistically, that's not typically how things are set up. So let's look at this example. So let's say we're starting out with 5 molecules of C4 and 8 molecules of O2. Which one is limiting? Now we can't just look at this and make the determination to say that we have less moles of CH4, so therefore that's limiting. Because really what we have to look at is the fact that we need 2 O2s for every 1 C4. So you can't just also look at it and say, I have the least amount. What you have to do is predict the amount of products you're likely to make using both of those starting materials and the amount that you have. So because it's not 1-to-1, we see that for every 5 molecules of CH4, we need 1 molecule of CO2 is going to be made. So that's going to be 5 possible CO2 we could make based on the amount of CH4 molecules that we have. And if we look at our O2, that means we could possibly make 4. So even though we started with less moles of CH4, because we need 2 moles of O2 for every 1 mole of CH4, it actually turns out that our limiting is our O2 molecules. So again, you really have to do these calculations. It's really not inherent that you can just look at it and figure it out. So what you need to do is, for each reagent, for the amount you have, calculate, based on your relationships, the amount of possible product. And then compare whichever one gives you the least amount of moles of possible product, that's your limiting. Not the most, because once we run out of the limiting, we cannot make any more. So calculate our least amount of mole of product. So our least amount, our limiting in this case, is going to be our 8 moles of O2. And our excess is going to be our methane gas. We have more methane left over once we get this final product. And our theoretical yield, if our O2 and our O2 and CH4 completely reacted, would be 4 molecules. And we're going to relate this to moles instead of molecules because you're never going to have 4 molecules in a sample. You're going to have a lot more than that. That's why we use the mole relationship. Remember, 1 mole equals 6.022 times 10 to the 23rd molecules. So that's a big number. That's why we use the mole relationship. So looking at this one, if our reactant is not completely consumed, it's our excess. That's what we have left of after. So let's actually apply this to an example. Now again, remember, if this gives you mass, you must convert it to moles because your relationship on your equation is in moles, not mass. So let's say we have this equation. It's given to you. It's already balanced. You can double check that. We want to know how many possible moles of Si3N4 can be made, and we're told two different amounts of our two starting materials. So we're going to have to convert the moles of our product from starting material A and the moles of our product from starting material B and compare them. And when we compare them, whichever one's the least amount, that's our amount of moles that's possible. Again, remember your pizzas. We can't make 5 pizzas because we only have enough sauce to make 3. So we're given how much moles of each of our starting materials we have. So we have 1.2 moles of silica and 1.00 moles of N2. So that's what we're given. And we want to find how much possible moles of our product, and our product is Si3N4 specifically, but that's our only product in this example. So our conceptual plan, we're going to have to convert both of those to our possible product. So we're going to convert our moles of silica to our moles of product, and then our moles of N2 to our moles of product, and we're going to compare those two amounts. The smallest amount of moles is going to be the limiting the theoretical yield. So let's do that solution. Let's work with silica first. Now this is already in moles, so we don't need the molar mass. But if we wanted to know grams, we could calculate that of our product. So we're starting with 1.20 moles of silica. And according to our equation, which is right here, that for every 3 moles of silica, we'll form 1 mole of our product. So we want our 3 moles of silica on the bottom and 1 mole of product on the top. So our mole silica cancel out. Now again, don't interchange. My coefficient 3 is always with silica. My coefficient 1 is always with Si3N4. Don't switch it. So this tells me I could possibly make 0.400 moles of our product. But I'm not done because I need to calculate how many moles of our product I could possibly make with my other starting material. So I know how many moles of N2 I'm working with, my nitrogen gas. And I see that it takes 2 moles of nitrogen gas for every 1 mole of product. So my 2 moles go on the bottom, and they cancel out, and of course that comes out to 0.5. So which one is my limiting reactant? Silica is my limiting reactant because this is going to be my theoretical yield. I cannot make more product because once I run out of silica, I can't do any more reaction. So whichever one is the lowest number of moles product, that's going to be your limiting reactant. And that amount of moles of your product is your theoretical yield in moles. You could also calculate your theoretical yield in grams by using our molar mass of Si3N4. Go away. So one more thing we're going to touch on before class ends today. For the last 5 minutes of class. So back to our pizzas. We calculated based on the amounts of stuff that we had that we could make 3 pizzas. But let's say something happens and for some reason we only make 2 pizzas. You drop one on the floor, you burn one, something happens. So you could have made 3 pizzas based on all the material you had, but you only made 2 pizzas. So you didn't get 100% yield of your product. You only got a certain percentage of that. So that's what we call our actual yield. The amount that you actually recovered after you did the reaction is your actual yield. You can't calculate your actual yield. That has to be found. After you do the reaction, you have to measure your product, see what you made. So I would have to give you an actual yield. But once we know our actual yield, then we can calculate our percent yield. Our percent yield is just our part of our whole being our theoretical yield, what could we have made. And then we're going to take what we did make, divide by what we could have made, and of course, multiply by 100. Now, you cannot make more than your theoretical yield. So, your percent yield should always be less than 100. And you have to be a really, really good chemist to get 100% yield. Typically, you'll recover because you have to separate things, you have to isolate things, measurement issues. You'll usually get under 100% yield because of measurements and things like that, and sensitivity of your instruments. So 99.9% yield is usually pretty good. But that's what we're looking at with our yield. For some reason, you might not be able to make 100% yield. So in our case, this is 67% yield. So to determine our theoretical yield, we use our stoichiometry. To determine our actual yield, that's what we actually measure. What did we actually make from the reaction? And that has to be given or measured from your reaction, of course. But your theoretical yield always comes from your limiting reagent. Now, you can have your theoretical yield and your actual yield in moles and get your percent. Or you can convert them both to grams and get your percent. But your theoretical yield and actual yield have to be in the same units. So they can both be in liters, that's fine, but they have to be in the same units because our percent has no units. So your theoretical yield can be in moles, it can be in grams, your actual yield can be in whatever. You'll get the same number as long as they're in the same units. So that's key when you're doing that. So of course, 110, it can't be 110. You won't make more than what you predicted unless you did something very wrong. So you guys have a great day. Stay dry. I will see you on Wednesday.